these bonds and start calculating the energies at those different geometries, what happens? So essentially what should happen is this black curve over here, where when I have pulled apart the bond really far away, essentially the hydrogens are not interacting with oxygen anymore, and it should plateau off the total energy. However, if you use traditional quantum chemistry methods such as coupled cluster or MP2, the curve looks like this red one or the blue one, which is of course strange because such activity in energy should not happen when the atoms are less interacting at that limit. Furthermore, if I look at the errors, this is what the errors look like, and at infinite separation, essentially the calculation does not converge and the errors are infinite. So why is this happening? That's essentially due to the strong correlation between the electrons, which hasn't been taken care of in the reference calculation. And here the reference calculation is of course the mean field Hartree-Fock form. Since I have not taken into consideration any correlation during that reference calculation, any perturbative approximation on top of that is bound to fail if the perturbation is large. In other words, if the correlation is strong. This sort of an effect shows up in excited state chemistry, which I am largely interested in, diradicals, triradicals, essentially any polyradical systems, transition metal complexes, polyenes, graphenes, which is again something I'm going to touch upon in this lecture, and metal clusters, and a plethora of other systems. So that's really bad news for quantum chemistry, that this kind of evil effect shows up so much. So what really is this effect? So from a quantum chemistry perspective, we generally like to think about orbitals. If we have the orbitals like so, and these are just the orbitals with increasing energy, if we have, let's say, 6 electrons like here, we will fill up the lowest 3 orbitals, and then all other orbitals is going to be empty. That's how a chemist looks at this picture. This is a single reference, nice simple picture. There's a gap between the highest occupied molecular orbital and the lowest unoccupied molecular orbital, this delta E over here. But what happens when there's a large degree of conjugation or something like that, where this delta E becomes really, really small? When that happens, the electrons doesn't really have any reason to just stay in the highest occupied molecular orbital only. It will start visiting these higher orbitals. In other words, there will be more than one reference electronic configuration. That situation is what we call multi-reference or multi-configuration. So now one might think, okay, fine. As a chemist looks at this, if I take all the valence orbitals, not the really low down orbitals or really high up orbitals, but the valence orbitals, and take all possible combinations, then I should be able to take care of all chemistry that one might be interested in. I'm always looking at low energy, low lying states chemistry. I'm never really blowing the molecule to smithereens, right? So those phenomena should be easily viewed. That's what one would expect. Let's see how that works out. Now here, let's say I take the example of this acene system. So this is a pentacene, and this is a, I don't know, I think it's a decacene. So as the system size increases, I will show you an effect of the strong correlation and how we can deal with this. With that example, I'll basically structure my talk around that example. So what happened in 2004, there were some DFT calculations which is a mean field calculation. It predicted that the singlet triplet crossover happens in these acenes, which basically means that as the system size increases from pentacene to hexacene to heptacene and so on, the triplet state becomes more and more stable, And in fact, it becomes more stable than the singlet state. However, in 2007, when all possible configurations was included, you know, the multi-reference thing that I was talking about in the last slide, and in doing so, a method called DMRG was used. I'm going to explain the method in a little while. It was shown that the major effect of this was static correlation, and then there was no singlet triplet crossover due to presence of static correlation. In 2010, it was shown that using CCSD parenthesis T calculations, it was shown that dynamic correlation is actually a big player, and still there is no crossover, but it is due to dynamic correlation. And in 2015, our group showed that both static and dynamic correlations are important. So it seems that to understand chemistry, these small details seem to be quite important, and we need to include all of that small effects to understand chemistry in all its complexity. So now let's go to the challenges of calculating these singlet triplet gaps. Let's say again I take these systems. In these systems, the number of configurations, so number of ways I can put the electrons in the valence or space, is an exponentially scaling problem. What I mean by that is, let's say if there were 30 carbon atoms, 30, then there would be 30 pi orbitals, and in the valence space, and in those 30 pi orbitals, there will be 30 electrons in the valence space. That valence space, the number of configurations one can think about in that valence space is of the size 10 to the power 33. Now, a matrix diagonalization of this size, taking that matrix diagonalization is an n-cube scaling problem, it would be 10 to the power 99 operations. That's a very large number of operations, especially when I compare it against the total number of atoms in the universe, which is 10 to the power 82. So there's no way, basically, we can kind of go on and take all possible combinations and configurations and look at it in such a, you know, brute force kind of a way. So that's one major problem. Let's see why it grows exponentially and how we can deal with it. Let's take this cartoon example of a spin system. Spin system, unlike orbitals, it's just, there's two possibilities. The two possibilities of a spin state are, it can either be up spin or down spin. So if there are two sides with spins, there will be 4 possibilities. And if there are 3 such sides, there will be 8 possibilities, which basically means it's 2 cubed possibilities. So you can see that with the system size n, it is going as 2 to the power n. So if it was a essentially an orbital system, it would be 4 to the power n. So whatever is the dimension of each side, to the power whatever is the system size, and therefore this is an exponentially scaling problem. So how can this be written in the exact form? In the exact form, this wave function, this exponentially scaling wave function, is called full CI, of course, and it is written in this form, in the occupation number formalism. These are all occupations of orbitals or positions of spins, whichever way you look at it, and this is the coefficient in front of it. So all possible occupations and its coefficients, how important are those configurations? That's the essential idea. And in the matrix product state language, this can be depicted as this comb-like structure. So essentially, this is the tensor, and this tensor has so many dimensions. So each of these things sticking out, that is the dimension. So let me explain the matrix product state language in a little bit more detail. In the matrix product state language, a real or a complex valued number can be shown as just a circle with no legs sticking out, because it has no other dimension. It's just one number. So there is no dimensionality associated with it. So there is no leg sticking out of it. If it's a vector, it has a dimension. There's a there's a I index. So according to that index, there is one leg that denotes this index I. If it's a matrix, it has 2 dimensions, so there are 2 legs. If it's a tensor, it has 5 dimension, let's say, this is what it would look like. Now notice, it does not matter what is the shape of the circle or oblong or whatever it is. And it doesn't matter where the legs are sticking out from. It's just how many of those legs that are sticking out. That's the only thing that we are concerned about. That's how we basically look at these matrix product state pictures. So therefore, if I am going to do a contraction or matrix vector multiplication, this is what it would look like. So this is the matrix with 2 legs, and this is the vector with a single leg, and I am summing over this index, the jth index. So that is the one that is common between these two. And after I've done this operation, essentially I'm left with an object which is whatever shape, but it has only one leg which is sticking out, because after a matrix vector multiplication, I'll only have a vector that is left. So if similarly I'm performing a trace operation, this is what it would look like, because this, after taking a trace, there is no dimension that remains. There's no sticking out leg anymore. So this is essentially the language of MPS, or matrix product state. So in this language, therefore, this is the full CI wave function, this comb-like structure, and therefore this is an n-dimensional, whatever is your system size, that many dimensional tensor, d to the power n. So the number of terms inside this oblong is essentially d to the power n. If I perform a singular value decomposition, taking all index from in the right side as a kind of a combined index kind of a stuff, and this index is kept separately, and I take a singular value decomposition in between, then what I have is, after singular value decomposition, this is what it would look like. This is a diagonal matrix with 2 legs. This is a matrix, and this is a tensor which has a fewer dimension than the previous tensor. And therefore, if I keep doing these singular value decompositions over and over again, I can finally arrive at this matrix product state ansatz. So now I have a matrix times a tensor times a tensor times a tensor, and so on, and finally a matrix. So what does it really mean? Each of these positions are the real position of the lattice of sides, or the lattice of orbitals, or whatever I am trying to calculate. And these dimensions are the real dimensions where I can say, okay, this orbital has 1 electron, then I will put 1. Or this spin is up spin, then I'll put +1. This spin is down spin, I will put -1, and so on. So once I have assigned values to each of these legs, now you see this thing reduces to a number. After a lot of matrix multiplication, it basically reduces to a number, which is this number. So I'm essentially kind of massaging this weird object into an object that I know how to deal with, because I know how to deal with a few dimensional objects rather than a many dimensional tensor. And furthermore, if this singular value decomposition, after I perform this singular value decomposition, if I look at the singular values and retain only the most important singular values, I may be able to reduce the dimension, the total number of terms that are in this expression. So from d to the power n, I can go to a system size, which is, if each of these dimensions are m, then I can go to a system size which is n times d times m squared. So now with system size, this scales as just linearly. So essentially I have performed an exponential shaping. Of course, the catch over here is that this number of states retained, or the number of singular values retained over here, this m, needs to be reasonably small. Otherwise, I still have a very large number. I've just written the large number in a different way. Okay, so this is essentially the crux of the matrix product state ansatz. And the reason why we like to draw these rather than write the equations is because if you look at the expression for this matrix product state ansatz, this is what it looks like, with so many indices and so many numbers and stuff running around all over the place that it becomes a bit difficult to do the bookkeeping and to understand what is going on. That is why this pictorial scheme is often used. Now, density matrix renormalization group actually gives us a nice way of finding this matrix product state, because I've just shown you an ansatz. This is a nice way of writing the wave function, but I still don't know what each of these terms are, what each of these matrices are. So to put values to each of these objects, there's an algorithm called the density matrix renormalization group. As I had shown before in the previous slide, that this is the exponential scaling that would have happened if one didn't perform any tricks in between. So what DMRG does is, after you have basically taken all possible combinations of states between two sites, which is here 4 in this case, you look at the density matrix of the full system with all possible combinations of only the first two. You take that density matrix and then perform singular value decomposition and retain only the most important states. So you basically reduce the degree of freedom by a step called decimation. So you have reduced the number of degrees of freedom from 4 to, let's say, 2. Now with these two states, you can again increase the degree of freedom with the next possible site by a step called blocking, and then again further decimation and so on. Please note, this is a cartoon, that it won't remain 2 always, but it will still remain a tractable number of states. It won't become exponentially scaling, hopefully. So that's essentially what the DMRG algorithm does. Again, in the algebraic notation, this is what a full CI wave function will look like. For orbitals, it will have a scaling of 4 to the power n, not 2 to the power n, because 2 to the power n is only for spin states. If it were a mean field approximation, essentially there are no correlations between sites. So you are basically taking a product of the orbitals. Of course, you are antisymmetrizing it, but other than that, there's no correlation between them. And the DMRG wave function, or the matrix product state wave function, looks like this, where this is the auxiliary index, which is basically carrying the information of entanglement from the first site to the second site to the third site to the fourth site, and so on. And it is in the dimension of these auxiliary indices that the fact whether DMRG will be a good algorithm or not, that's what this dimension is what determines that. As long as the dimension of this matrix product is small, this gives a good general ansatz that is also economical. Okay, so let's try and use this ansatz and see what that gives us. So for these ACN systems, actually we have done this calculation. Actually, even before us, many people have done this calculation of the singlet triplet gap. This is what it looks like, this exponential decay. On the other hand, we tried few other polyaromatic hydrocarbons, because at that point we were trying to look at finding small polyaromatic hydrocarbons where the singlet triplet gap can be very little. So if we are trying to find magnetic materials. Okay. So if I take a polyazulene, so you see there's a 7-membered ring and a 5-membered ring and so on. So the polyazulene, the singlet triplet gap goes like this. And the fused acene azulenes, which is a system that looks like this, here the singlet triplet gap falls off much more quickly. And in fact, this is the 0. So there is indeed a singlet triplet crossover, as in the triplet state becomes more stable for fused acene azulenes with system size 6 and higher. So this is indeed a very small molecule polyaromatic hydrocarbon that can have a stable triplet state. But then we are, again, since we are quantum chemists, at that point we ask the question, why? Why are the singlet triplet gaps low? How can we predict, without doing these really heavy calculations, why a singlet triplet gap will be low or high? So we looked at the correlation between the diradical nature and the singlet triplet gap and found nothing. As you can see, this curve is definitely does not show any correlation whatsoever. But that means some of our simple orbital picture that a chemist carries in their mind is sort of falling apart. Let me explain how. So let's say I have the HOMO and the LUMO, where the HOMO-LUMO gap is pretty high. Then the singlet triplet gap will also be pretty high because it is the difference in energy between this state and this state. On the other hand, when the singlet HOMO-LUMO gap reduces, the singlet triplet gap also should be lower. But also similarly, now the diradical nature, as in one electron here and one electron there, will become more probable because this gap has kind of closed down. So now the electron can hop to the next available orbital much more easily. So one would have expected from this picture that as the HOMO-LUMO gap decreases, the diradical character of the wave function should increase, and similarly the singlet triplet gap should decrease. But that's not what is going on, as we saw from the previous slide. So essentially the mean field approximation is completely breaking down. Actually, this is a very interesting story. So let me kind of give you a bit of the story, and then we will go to the rest of the algorithmic developments that we did. Around this time, we actually came across this paper by Ramsesha and co-workers, which mentioned a frustrated two-leg spin ladder. Now, this is the system that this paper is talking about. How is this system similar to a fused AC nazolene? You can see, basically, this is a 7-membered ring. This is a 7-membered ring. This is a 5-membered ring. This is a 5-membered ring. So essentially, the connections are actually absolutely similar between this polyaromatic hydrocarbon and this skewed rung ladder. So, and what these guys actually figured out is that in these skewed rung ladders, there's a lot of spin frustration going on, and that's why they can take different phases of different magnetic phases. So we thought that maybe that's what is going on. So firstly, what is spin frustration? Well, if we have a spin in a triangular lattice, let's say, and they are antiferromagnetically coupled, which basically means the spins want to be at opposite spins to each other. As in, if I have a spin up, then the next one, adjacent one, wants to be spin down, and so on. So if it's a triangular lattice and I have placed 2 spins, one up spin and one down spin, they're happy with each other because they're next to each other, they're opposite spin, everything is fine. But what happens when I try and put a spin over here? Because if it is happy with respect to this one, as in if this is a down spin, then it is unhappy with respect to this one. If it is happy with respect to this one, it is unhappy with respect to the other one. So this is essentially what is spin frustration. And similarly, if you have a non-collinear situation, the spins will just be, you know, at 120 degrees with each other. So what we did at that point is actually, instead of looking at orbitals and the quantum chemist way of looking at it, we kind of reduced the complexity of the Hamiltonian. And in doing so, we removed all the lattice degrees of freedom, that is the variations in bond lengths. And we removed further details of the molecular Hamiltonian and took a simple spin Hamiltonian like so, which essentially means all the bonds are equivalent and only nearest neighbors interact. And because they're antiferromagnetic coupling, it's like paired up spins that we see in quantum chemistry. With with those model Hamiltonians, which we had kind of parameterized, we did the calculation for these same systems, but now in model Hamiltonian. And here you can see that the qualitative nature is retained, as in this is still faster decay, this is still slower decay, but many of the quantitative features are not quite the same. So we don't actually see spin crossover here, but the qualitative trends are still really close. So we wanted to use this not as a quantitative handle, but to qualitatively understand what is going on. because we ask two questions always. We ask what is the value, and then we ask the question why. So what is the value we can get very accurately from the DMRG type of calculations, but why is not so easily found, because the wave function we arrive at is so complicated that we cannot analyze it all that simply. So from the model Hamiltonian calculations, in fact, we found out that, you remember those configurations I was talking about of electrons? Now we have the configurations of spins. In this configuration of spins, we found that the most important configuration for a scene is this one, where all up spin, or this plus, is always flanked by a minus or a down spin, and a down spin is always there are adjacent up spins. So everybody is happy with everybody. There is no spin frustration. However, when we have a fused when you have a polyazulene, you see there are spin frustrations here. So there are same spins which kind of come and accumulate in a few of the common bonds, not all common bond, but a few of the common bonds. And in the fused acene azulene, in fact, this effect is even more pronounced. There are many places where these common bonds are spin frustrated. So it's essentially, it's these spin frustrations which we propose is pushing up the, or rather reducing the stability of the singlet state, and therefore the singlet triplet gap is decreasing. In fact, one shouldn't actually jump to this hypothesis from just the most important configuration. We have taken these spin densities, and this is what it looks like. So again, we see that the same spin densities kind of accumulate in the common bonds, and that's what leads to this effect of singlet triplet gap reduction. But again, at the end of the day, I'm a quantum chemist, so I don't really know if the model calculations are all that close to the molecular calculations, and therefore I try and look at signatures of whatever we are proposing in the molecular calculations. So we looked at the geometries, the optimized geometries of these molecules. Here what we see is that there are these short bonds and long bonds, those kind of alternation in the acenes. This is already known. This appears kind of a distortion because of symmetry breaking. However, when we went and looked at the polyazulines, we see that there are, these bonds are almost these common bonds where we saw the same spins coming and accumulating. It's like the same spins came and they are exerting a repulsion kind of a force because it is antiferromagnetically coupled, and they are leading to increase in bond lengths. So here you see the bond lengths are increasing quite a bit. It's almost like a single bond, very close to a single bond. In case of fused acene azulines, the number of such single bond like things are even larger. So this essentially, our hypothesis is in fact confirmed by the signatures that we find in the molecular Hamiltonians. So far so good. So till now we have actually, I have shown that we have a computationally affordable method to screen molecules using model Hamiltonians, and a computationally affordable way of calculating accurate singlet triplet gaps using DMRG and matrix product state. But here at this point, let us get a bit more ambitious and try to extend this kind of a reasoning to two dimensions. Instead of one-dimensional polyaromatic hydrocarbons, if I have a two-dimensional lattice, something like this, like a nanographene or something like that. So what is the problem with extension to two dimensions? Well, firstly, what was saving us, what was enabling us to do the DMRG efficiently and have a matrix product state with small values of M is basically if I was going from one side to the next one, to the next one, to the next one, always in between the amount of entanglement was the same. So it was not growing with system size. I can have 5 such sites or 10 such sites. Always the left and the right, the kind of the area between the left and the right, the amount of entanglement was always the same. But if I have a 2-dimensional lattice like this, and if I cut like this, if I have a 5 by 5 system, my entanglement is whatever it is for 5. If I have a 10 by 10, it will be whatever it is for 10. So basically the amount of entanglement is growing. If the amount of entanglement is growing, the number of states I need to retain, that M, will grow with the system size. Alternatively, I can even think that, okay, I'm going to do DMRG like a snake. So I'll go like this and then kind of snake back like this. That's actually what is done generally in these situations. But you see, this 1 and 10, these sites are actually, they are adjacent to each other. But when you are doing the calculation, this comes across after a lot of steps. So you have essentially lost all the entanglement that you would have retained between 1 and 2. As efficiently as you would have retained between 1 and 2, you cannot retain between 1 and 10. And therefore, again, either you need to bump up the value of M quite a lot, or you will basically lose precision. So MPS is a great way to go, but only for one-dimensional system. And similarly, DMRG is a fantastic algorithm if it is a one-dimensional or a pseudo one-dimensional problem. In other words, as long as the dimension of the matrix product is small, this gives a general ansatz. But there's another part that is, this is also second thing that we should always remember, that this is a variational optimization. So let's look at what really a variational optimization would mean. It would definitely mean calculation of energy repeatedly, because I will take a derivative with respect to energy in some form or the other, and optimize the coefficient somehow. So if I want to compute overlap of a matrix product state, this is what it would look like. And in our calculation, we'll basically perform something like a bubbling algorithm, which basically means I will first do this contraction first, and then I'm left with only 2 indices that are sticking out. Then I will again go here and do all the summations in between, this one, and this one. Again, what I'm left with is only these 2, and I'll keep repeating that process. So this bubbling kind of an algorithm is going to keep my computational scaling kind of system size independent, or rather it won't grow exponentially on me. The system size dependency will not grow exponentially. If I were doing the same thing for the energy expectation value, instead of just taking the the matrix product state and its complex conjugate, I would take some operator in between. Basically, I'm taking an expectation value, so it will be an operation like this. So that is a little bit more complicated than a computation of an overlap, but not terribly so. Okay, so this is essentially what MPS computation, energy computation looks like. Now let's go to a 2-dimension, and let's say instead of 1-dimensional MPS, if I had a 2-dimensional some tensor network state, what that would look like. This already looks horribly complicated. So this blue things over here, this is the tensor product state. Because it is 2-dimensional, I have broken in all directions. So if I actually did that, then with system size increase, essentially when you see how the complexity is increasing, how this bubbling kind of an algorithm is out of question, and all algorithms will actually start scaling quite a lot. And therefore this computational scaling, as I mentioned even 2 slides back, is essentially due to the area law of entanglement. And so going forward, somehow we have to avoid computation like this. One way, so what I'm trying to say is, if I kind of not take an MPS, which is good for only 1 dimension, but take a 2-dimensional tensor network state like this, I need to be able to avoid calculating an expectation value. But a variational algorithm always makes me calculate an expectation value. So what is the alternative here? The alternative at that point, what we saw, we came across this paper by Carleo and Troyer in 2017 Science, where they showed that a tensor product state is actually well represented by a restricted Boltzmann machine. Restricted Boltzmann machine is nothing but a very special kind of a neural network. So we didn't know restricted Boltzmann machine all that well. So what we thought is, okay, we understand what a neural network is. Neural network is nothing but a matrix vector multiplication with some function stuck in front of it. So this is the activation function, and this is a matrix vector multiplication. This is the matrix, this is a vector. So that's all that there is. So if I take an input vector, I multiply it with a matrix, the weight matrix, I get a next vector. I put that activation function, go to the next layer, keep doing this till I go to the output. And all I'm doing is tuning these parameters in between. So if a tensor product state can be represented by a neural network, it should be trainable. So we should be able to somehow use machine learning. Let's see how. Firstly, let me rephrase the optimization problem from a variational problem to a machine learning problem. Notice we had this tensor, really ugly tensor, the full CI tensor. This I'm going to approximate as a neural network ansatz, which basically means I have a function f of x, which is very complicated. Because I don't want to do a calculation on this f of x, I'm using this some kind of a, because I have a y of x, which is my actual function. But because this y of x is very complicated, this one, I want to represent it as f of x, which is easier on my computational resources. And in this specific case, I'm writing this f of x, or the approximate function, as a neural network. So matrix vector multiplication. Why? Because f of x is extremely flexible. Well, neural networks are extremely flexible. And the next constraint I'm going to put on it is that the values of f are going to be close to y for whatever training data I use. And I will also choose the simplest form of f of x, because there is no point making the problem more complicated than it already is. So this is essentially the approach that we are going to take. Here, the f of x is written as this matrix W, weight matrix, times the input. Input is either the occupations of the orbitals or the spin states. So that is my input. I multiply that with some tuning parameters, I get my final function. So instead of minimizing this function f of x with respect to W, instead of minimizing with respect to energy, we minimize with respect to some data. But what data? We don't have any data. If somehow we could get our hands on a few known weights or a few known CI coefficients, so at that point, we would be able to optimize the coefficients W with respect to those CI coefficients. Well, what is the benefit? Of course, we don't have to calculate the energy, but there is still this sticky point, where do I get the CI coefficients from? So as a toy problem, we first constructed the network as is. I'm not going into the details here. And we took a full CI space. From that full CI space, can I train the full CI space again? Which is actually a stupid problem, but it's still a proof of principle that whether it at all works or not. In fact, we see that the training can be done. And from the errors of the CI coefficient, they're actually quite low. So it is trainable. Okay, good. In fact, it is trainable. And next thing what we did is, instead of going from the full CI space, we took a very truncated CI, actually a Monte Carlo CI, a very smaller subspace. And from that subspace, we tried to train the full Hilbert space. That's what's done over here for the polyaromatic hydrocarbon tetracene for a two-dimensional system with 4x4 sites and so on. And here you see for this one, after quite a few different networks and so on, we figured out that we can indeed train it quite well. The errors are quite low. And the trick to that is to separate the training of the magnitude and the sign of the CI coefficients and all that. These are just small tricks. But at the end of the day, it is indeed trainable, and it is trainable not just from the full CI space, but from a much more smaller truncated space. So I don't need to do an initial CI to get initial full CI to get the data for training. And I, of course, also don't need to do an energy computation. With that, we have calculated the training energy. This is the training space energy. So training space energy, you see, is much higher than the full CI energy, the red one. These are the variational energies we calculated from the machine learning model. And you can see that this is getting very, very close to the full CI energy. So that's all great. And here it is shown that it works for quite a few different variety of systems. But our idea is not to understand or learn CI coefficients and CI expansion, because CI expansion is anyways scaling, it scales badly. So the learning exercise or the amount of learning data will also scale badly and will be in trouble again very quickly. So we have to learn the matrix product state ansatz. And in fact, there is a paper in, actually now it is there in Neuro IPS. In arXiv, there's a paper by Staudenmayer where they have shown, they have used MPS ansatz, this kind of a function, not as a wave function, but as a way of training handwriting recognition. So we used those ideas and tried to train a matrix product state as a wave function. And the algorithm that is used is actually very similar to a 2-dot DMRG algorithm. I have not explained the DMRG algorithm in so much detail, but it is very similar to a DMRG algorithm. And as I mentioned before, there is no need to compute energy or any matrix product operator. So that's all great. Here we see for a 18-side chain, one-dimensional chain, which is actually again a toy system, we see that the sensitivity and the specificity with different size of M of the MPS is increasing. So here for if M is kept at 50, in fact, the sensitivity and specificity are both quite high. Sensitivity denotes the ability to detect important configurations, and specificity is the ability to detect unimportant configurations. If both are there, then I can easily separate out which is important and which is not. I can take only the important configurations, and therefore that's all that matters. So by using this matrix product state as a screening for CI coefficients, we can still train a matrix product state ansatz. And again, you see very good accuracy with respect to full CI numbers. This purple curve is the full CI and the green is our trained MPS energies. And furthermore, it is actually very system neutral. This is a kind of two-dimensional system, and this is a very one-dimensional system. You see that efficiency is almost similar for both. This paper is right now just about available in chem-arXiv. We have submitted it, but it's still open access in chem-arXiv. And furthermore, we have also looked at the energy versus cost function, which says that how good is this MPS as a wave function? I can probably screen the CI coefficients, but can I use that as a wave function ansatz? Here you see that the cost function and the energy decays almost identically for this system. So indeed, this matrix product state that is not variationally optimized, but rather machine learning optimized, is actually a very good proxy for the variationally optimized MPS wave function. So that's all great. So where are we headed with this? The whole idea was not to do this for MPS, but to be able to do it for a really two-dimensional network where calculation of energy is complicated. So our next goal would be to apply it to Hoombs tensor network and PEPS kinds of networks to train them using this machine learning algorithm. Just to give you a connection between these Coombe tensor and some of the chemical system. So this iron sulfur complexes, they can actually be put in a nice Coombe kind of a way. So each of these are like, these are sulfur orbitals, or these are all iron orbitals like that. So they are more strongly entangled between each other and sort of less strongly entangled with the next set of orbitals in the next atom, like that. So these were networks that have already been designed. The networks are already designed by Stephen White, but their calculations are extremely expensive because they did a variational calculation. And now we are in a position to actually do the same using the machine learning approach. So to conclude, I hope to have convinced you firstly that variational optimization of MPS is a good way to understand strongly correlated system, and DMRG gives us a very strong algorithm for that. It is efficient for one-dimensional system, and the extension to two-dimensional systems is of course possible via artificial neural networks. But what is more attractive to us is that machine learning of MPS is even more computationally efficient route, and we will take this to more complicated tensor product states soon. I need to acknowledge my students. This work was done by Madhumita, Shumunto, and Mondira, my 3 PhD students. And this is my group over here. And funding from various sources were also instrumental in making this happen. Thank you.
Okay, thank you, Professor Ghosh, for such an interesting lecture. So now the session is open for questions. Please, anyone can ask questions to Professor Ghosh. Okay, I think there is no questions, Professor Ghosh. So with this, we again thank Professor Ghosh for such an interesting talk, and thank you very much. Now, the quantum chemistry section of QIQT 2022 in the second part ends today.